We're going to start at the very beginning and review the periodic table of the elements. So if you want your periodic table to look at, that would be helpful. So today we're just going to review how to read the periodic table of the elements, what each and every piece and part of this means to us, and what it tells us. So in this periodic table of the elements, you'll see there's a key. The number at the top is the atomic number. And then underneath is the elemental symbol and an element name you'll have. That's why there's no excuse to misspell any element names. And then we have the average atomic mass next. So those are the things that we can read directly off the periodic table of the elements. There's also some things that we can interpret from the periodic table of the elements. So I'm just going to pick an element out of random here. Let's pick iron. We're all familiar with iron. We've all seen iron before. So on the top of iron, there is a 26. That means that there are 26 protons that each have a +1 charge. If we have an atom of iron, it also has 26 electrons. Now we'll look at the average atomic mass. The average atomic mass is going to be the one with the decimals. That means if you take all of the different isotopes, you take lots of different, huge sample, lots of different isotopes in there, it will have an average atomic mass of 55.85. That means if I take an entire mole, which we will learn more about as soon as we come back from winter break, it will have a mass of 55.85. So a mole is 6.02 times 10 to the 23rd particles. In this case, 6.02 times 10 to the 23rd atoms. 6.02 times 10 to the 23rd is such a huge number. It is very difficult for us to wrap our brain around how big that number is. We will spend some time trying to understand it when we get back. Because the mass number is the number of protons plus the number of neutrons. So the average atomic mass is the number on the periodic table of the elements with the decimal points. The mass number is the number of protons, which have a positive charge, plus the number of neutrons, which have a 0 charge. Those each have a mass of 1. That means that there's not a single atom that has a mass of 55.85. You either have iron 55 or iron 56. There's some other isotopes too, but we don't need to worry about all of the isotopes. Iron 55 still has 26 protons, just like iron 56. If it doesn't have 26 protons, it is not iron. So what it differs by is the number of neutrons. So this particular iron with a mass of 55 would have 29 neutrons. Because when you add them up, it has to equal the mass number. This particular iron has 30 neutrons to add up to 56. Does anybody remember what is it called when you have two atoms that have the same number of protons? They are the same atom, but they have a different mass. Those are isotopes of each other. So atoms that have the same number of protons but a different number of neutrons are called isotopes. Let's pick a different one. I'm going to do sulfur. If you look at sulfur, sulfur is number 16. That means that sulfur has 16 protons. That's the atomic number. The atomic number is the identity of an element. In order to be sulfur, it has to have 16 protons. The average atomic mass is the one with the decimal points. We read that right off the periodic table of the elements. And it says 32.07. That's how many grams you have if you have a huge sample, 6.02 times 10 to the 23rd atoms, which is a mole. You will have a tiny pile in your hand that has a mass of 32 grams. If I have an atom of sulfur, it also has 16 electrons. Remember when we talk about atoms, they're electrically neutral. They have the same number of protons as they do electrons. We can have two different isotopes that we're going to worry about. There's actually more isotopes, but there's sulfur 32 and sulfur 33. Sulfur 32 has 16 protons, just like sulfur 33. 16 plus charges. Sulfur 32 also has 16 neutrons, but sulfur 33 has 17 neutrons. These are called isotopes. These are the two isotopes of sulfur. When you take a sample of sulfur, when you take a huge sample of sulfur, most of them are going to have a mass of 32, but you're going to have some of them, about 7%, right, that have a mass of 33. Now let's go back up to these number of electrons. The other thing we can tell from the periodic table of the elements is what family it's in. It's in the oxygen family, therefore it has similar chemical and physical properties. In this family, it's labeled number 16, but it also has the Roman numeral 6. That tells us that sulfur has 6 valence electrons. Remember, everybody wants to be like a noble gas, so everybody wants to have a noble gas configuration. So he could either try to lose all 6 of his electrons, or he could gain 2 more to be like argon. If he gains 2 electrons to form an ion, he won't have 16 electrons anymore. Still sulfur, so it still has to have 16 protons or 16 plus charges. But if he gains 2 more, he now has 18 electrons or 18 minus charges to be just like argon. That gives him an overall charge of -2. So the periodic table of the elements also tells us that sulfur is in the oxygen family. He has 6 valence electrons. He is a nonmetal. Remember, nonmetals are gainers, metals are losers. He's going to gain 2 electrons and have a charge of -2 as an ion. We can also read that off the periodic table of the elements. And remember, this line right here, the stair step, is the difference between metals and nonmetals. These guys over here are all metals. Who can tell me a property of a metal? Yeah.
It's ductile.
Ductile.
Malleable.
Malleable. Anybody else?
Conductor of heat.
Conductor of heat.
Yes. Luster.
It is luster or it's shiny. Also conducts electricity, right? So shiny, ductile, malleable, conductor of heat and electricity. Also, they tend to be metal solids at room temperature. That means that they have higher melting and boiling points. It means that they're more dense. These guys up here are our nonmetals. Who can tell me how nonmetals behave? Yes.
They're dull.
Dull. brittle. Anybody else?
Insulators.
They're insulators. And let's also remind ourselves, metals are more likely to lose electrons. Nonmetals are more likely to gain electrons. Metals tend to be more dense. Nonmetals tend to be less dense. As a matter of fact, you can look and see a lot of the nonmetals tend to be gases. So this has to do with the electronegativity, ionization energy, atomic radius, so on and so forth. All of these things can be interpreted from the periodic table of the elements. So this is our first lesson that we learned in chemistry this year. Remember, we also learned our hot spots, our hot corners, which were fluorine and francium. Francium is the largest, most malleable, most ductile, most conducting. However, he doesn't hang around long because he can't hang on to his electrons, so he's either always in a chemical bond or trying to get into a chemical bond. So we don't refer to him all that often because he is so reactive that none of us have ever seen them. Go back up to fluorine. Fluorine is the most electronegative, meaning he's the best at taking other people's electrons. He is the smallest. He is the least metallic. And he has the highest ionization energy. So this is our first review lesson where we're going to kind of run over the things that we've learned throughout the entire year. The periodic table of the elements is definitely going to be on your final exam. I'm also going to add on to here real quick the electron configuration for our 16 electrons. So remember, when we do electron configurations, we start up here, we fill up the first principal energy level, then the second principal energy level, and then we'll go almost all the way through the third until we get to 16 electrons. So 1s2 represents the 2 electrons that belong to hydrogen and helium. 2s2 represent the 2 electrons that belong to lithium and beryllium. 2p6 represents the electrons that belong to boron through neon. 3s2, sodium and magnesium. And then if you notice, sulfur sits 4 positions into the 3p sublevel. So we go 3p4. If we want to do the abbreviated configuration, we go backwards to the previous noble gas, which is neon. And neon sits at the end of 2p. So if I put neon in brackets, that represents all 10 electrons that belong to neon all the way through 2p6. Then I have to represent the outer shell electrons, which happen to be my valence electrons. Those are my 6 valence electrons. When I do my dot diagram, I put my 2s electrons up here, and then 1, 2, 3, 4p electrons over here. If I were to do a box diagram, I would represent each electron with an arrow. Remember, the s sublevels have 1 orbital or 1 box in the orbital box diagram that holds 2 electrons. The p sublevels have 3 orbitals that hold 2 electrons apiece for a maximum of 6. Because of Pauli exclusion principle, I put 1 arrow up and 1 arrow down. 2 electrons cannot occupy the same orbital unless they have opposite spins. According to Hund's rule, we fill up with the lowest energy configuration as possible, which means that each sublevel gets 1 before anybody gets 2. So everybody gets first before anybody gets seconds. This last sublevel, I have to be careful. I put 1 electron in each first, and then that first orbital gets a second one, but the other 2 do not get a second one because I only can draw 16 arrows because I only have 16 electrons. This shows me that sulfur actually has 2 unpaired electrons, and he will form 2 bonds when he bonds with other atoms. Now, when sulfur becomes an ion and gains 2 more electrons, he will have a noble gas electron configuration, just like argon. So it's called isoelectronic with argon when he is an ion. So this is the sulfur 2- electron configuration. This will conclude the summary of these 2 lessons for today. Tomorrow we'll do another summary.